Science in Action. Science in Action is produced by the West's oldest scientific institution, the California Academy of Sciences, now in its 100th year.
Thank you. May I pour you a cup of coffee? While I'm doing this, I'd like to mention a problem that has arisen. Now, I didn't plan to drink my coffee right now. What I had hoped to do was to drink it in a few minutes. So the question is, shall I add the cream now, or shall I add it later, say in about 5 minutes when I get ready to drink the coffee? Well, we can very easily make an experiment out of this by adding cream to one of them now, and then later, when we get ready to drink the coffee, we can test that against the other cup of coffee to which we will add cream at that time. Now, of course, there will be a certain amount of cooling in both of these cups of coffee, and that cooling will be due to the flow of heat. Flow of heat from the coffee to the cup and from the coffee to the air. Now, there will be a considerable amount of difference in the temperature of those 2 cups of coffee in 5 minutes. I have difficulty remembering which one cools off the faster. But fortunately, we have as our guest on Science in Action a scientist who has the answers to all such problems. I'd like to have you meet him. He's an old friend of our program, professor of physics at the University of California, Dr. Harvey E. White. How are you there, Harvey?
Good evening, Earl.
Say, can you help us with this coffee problem?
I'm not sure about all the answers, Earl, but we'll try on this one.
Fine.
Here's a little diagram made up of 2 cups of coffee. This one hasn't had the cream added. It's black yet. This is the one to which cream has been added. Now, this cup here that's black started at the same temperature this one did, but being hotter, it cools off more rapidly. We can show that with a little graph here. Suppose this represents the cup of coffee that's black. It cools off with time, so that in about 5 minutes, 4.5, 5 minutes, it's gone down almost to room temperature, but not quite.
This would be the time scale here in minutes, 1, 2, 3, 4, 5.
That's right. Now let's look at this cup. The first thing we did was add cream.
Yes.
Right away, that cooled it down from this temperature down to about there. Then it started cooling, but being now cooler than the other one was, it doesn't give out as much heat per minute, and it follows a curve that looks similar, but always stays below the other one, goes along like this.
Oh, yes.
But now don't forget, we haven't added the cream to this one yet.
Oh, yes, the first one.
So now if we add the cream here at this point, it cools down below the other one and goes on.
Oh.
So now if you want your coffee to be hot at the end of 5 minutes, are you going to add the cream first or at the end of the time?
Well, the thing to do, quite obviously, from this graph is to put the cream in first, and at the end of 5 minutes, you'll have the hotter coffee than if you added the cream at the end of that period.
That's right. Just the opposite from what you might think.
Well, now, how does all this enter into the overall pattern of the transmission of heat?
Well, Earl, all of the various phenomena of heat transfer or heat traveling from one place to another can be classified under one of 3 classes of heat transfer, we call them. The first one is conduction, the second one is convection, and the third one is radiation. Now, conduction is a very, very slow process that takes place, as we'll see in our many experiments, over a period of time. It takes quite a while to conduct heat. Convection, however, is a more rapid process. But radiation is still more rapid, as we'll see later on.
Well, suppose we go back to that first one, conduction, and look at these various demonstrations that Bob Bell has set up here.
Well, here is a model, a crystal model, showing how the atoms would look in a solid. The reason for showing this is that I want you to keep in mind that all substances are made up of atoms and molecules. And it's the rapid state of vibration of the atoms and molecules that constitute heat. If you add heat to a solid, any solid, the atoms and molecules vibrate faster. If you allow it to cool off, the atoms and molecules slow down so that heat or temperature is a measure of how fast they're vibrating.
Well, how would that affect this pan of water under which we have the heat?
Well, when you go to heat anything, Earl, you have to bring it into contact or nearby something that's hotter. And here in this pan of water, we bring it up, bring a hot flame up from gas, burning gases, or from a hot plate. And the molecules of that hot object hit the molecules of the bottom of the pan and set them vibrating faster. They, in turn, hit others, and this atomic motion is conducted through the metal to the other side where it heats the water up.
Now then, on our chart that we have here, we would have the flame at this point, and then we would have the flame transferring the heat to the bottom of the container, and then from that, by means of this same atomic motion, into the center where the water is.
That's right. It's passing on of the atomic motion from molecule to molecule.
Well, this next demonstration that you have here is one that is really quite interesting. Now, let's see. First of all, you have a heat container here, and you have a certain amount of steam that's passing over through here. and down here. And then what are these various rods?
Well, this is to show, Earl, that some metals, some substances are good conductors of heat and others are poor conductors of heat.
I see.
Here are 6 metal rods, all the same length, all the same diameter, but they're made of different metals. This first one here is copper, then aluminum, and here's brass and German silver, tin, and lead. Now they're painted with a paint that changes color when they get hot. Although they're all heated to the same temperature down here at the bottom, you see this one has changed color all the way up already. It's been going about 5 minutes, and it is a good conductor, copper. But look at this one over here, lead. You see it's changed color only this far up, showing that it's a poor conductor. So here we have different kinds of conductors, good conductors, poor conductors.
And all metals, then, will have this sort of a characteristic. In other words, they will either be poor or good as far as
well,
conducting
some
is
in
concerned.
between. There are some semiconductors, we might call them.
Now, how about this cork experiment here? That is certainly a very ingenious
Well,
one.
this is another experiment in conduction, Earl. Here, I'm going to put a few drops of water in this little aluminum tube. This tube is mounted on the shaft of a motor. And I'm going to put a cork in the end of the tube now and stop it up good and tight. And now we'll put this wooden clamp around this shaft, and I'll turn the motor on. Now, what will happen is the friction will develop heat. It will be conducted through to the tube, to the water, and cause it to boil. And then I hope steam will develop and blow the little cork out.
There she goes.
Here it was the conduction of the heat through the metal to the water that caused it to boil.
Well, that's really quite a weapon there, the way that cork popped out. Of course, all of us know about the advantages of metals that are conductors, such as copper and some of these others we've seen demonstrated. Copper in electricity, that is an electric field used for wiring and that sort of thing. But occasionally we have need of other metals that are non-conductors, such things used in insulating, glass, wool, lead shields for X-ray equipment, wood, and various other things. But how about paper now? What sort of conductor is that, Harvey?
Well, paper, Earl, is a very, very poor conductor of heat. But curiously enough, even though it's a poor conductor, if you make it thin enough and distribute the heat over a large enough area, you can conduct a lot of heat through a thing like a thin piece of paper. Now, here's a very interesting little experiment with a piece of paper. This is ordinary typewriter paper, bond paper, folded into a little cup. Now, what I'm going to do is pour a little water in this paper cup, and I hope it doesn't leak, and we'll put it over this open flame. Now, don't be alarmed, Earl.
Now, let's see, there should be a scorch mark there. If anything's going to happen, I don't see anything at all.
Well, this paper can't possibly burn as long as that water's in there.
The water's starting to boil. Can we dump the water back in and see what the underside of that looks like?
Yes, let's try that. See, the paper's not scorched at all.
Not a thing there. Well, now, suppose that you had a thicker piece of material in the bottom of this. Would that make any difference? In other words, the heat would have to travel further through the material.
I anticipated this, Earl, and so I have another little box with a piece of cardboard in the bottom of it, see?
Well, that has cardboard in there that you put on top of the paper.
That's right. It's about 10 times as thick as that paper. Now, let's see if that helps us any. Put a little water in it and put it on over the open flame. Are you hoping it'll burn, Earl?
I'm just looking down here to see what... Well, I see a scorch mark appearing there.
It's
Well, let's
certainly
pour the
burning
water out.
There's
a scorch?
There's a scorch mark already. In other words, then the thinner the paper is, the more difficult it is for it to burn because the heat will be transferred through.
Yeah.
And yet the heavier paper here, the heat wasn't able to go through as readily.
That's right. Let's put this back on here and let it go a while. See if we can get the water to boil.
In other words, we come back to that later in the program. We'll find that the water's still boiling and the paper will not
I
be
think
touched.
that's a good idea. Mm-hmm.
Fine. Well, now this rod that you have here is another quite interesting one. Let's see. First of all, a piece of metal here. This is copper.
Copper.
And then hardwood here. And the next thing is what? A piece of paper around
Piece
there.
of paper again. Copper, remember, is a good conductor. The wood is a poor conductor. Now, I'll put the paper around it, too, and hold it tight against them and try to burn the paper.
Oh, yes. We have a scorch mark there. Let's take the paper up, and we see what happens. The scorch mark corresponds with the wooden area, but there's no burn mark on the copper part. Now, that,
That's
again,
right.
is conduction.
That's right. The heat flowing through the paper hits the copper, flows quickly into the inside of the copper because it's a good conductor. But here where it strikes the wood, the heat flows through the paper, hits the wood, and stops. It can't conduct it away fast enough. Paper gets hot and it burns. So here's a good conductor, a poor conductor, with a piece of paper around it.
This water, we've all seen how water can be heated. It's a poor conductor, and yet it quite often heats quickly over an open and hot fire. We see it happen, but just how does it happen and why does it happen?
Well, of course, water is actually a poor conductor of heat, and yet the pan of water will heat quite quickly due to the second method of heat transfer called convection. Now, convection current is an actual flow of hot water from one place to another. Here we come back to our diagram of the pan, you see, Earl. When the heat is conducted through the bottom of the pan, it heats up the water here in this area, and the hot water has expanded. And it, being lighter now, rises to the top. It goes up here toward the top of the pan. Well, if warm air water rises, cold water from the side has to come in and take its place like that. And again, cold water here comes down the sides to take its place, and in turn, cold water comes across the top. Now, you see what happens here? We have a current.
Oh, current is set up there.
A convection of current, of water, from the hot region here around continuously. And that's why a pan will heat up quickly.
Well, this is the same sort of thing that we have in lakes at various times of the year, and also happens in the ocean, these convection currents.
Yes, the warm water rises and gives us these ocean currents.
So now, what would be some practical application of these various convection currents?
Well, in this experiment, Earl, we're going to set up a convection current of water around this glass tube in the shape of the letter O. This is filled with water, and we're going to heat one corner here with a flame.
Yeah, we can move this right over there. There it comes.
And then to show that the water is going to flow, you see it's being warmed here, and being warmer it expands and rises.
Yes.
It'll go up the side of the tube and across over and down, and we'll get a convection current clockwise around this letter.
And this dye that you have then would indicate that.
That's right. In order for you to see that the water is moving, I'll put this dye in the top. See, there's quite a convection current there already set up.
Certainly going around there.
You see that all right?
In other words, a poor conductor such as water can be rapidly heated due to this convection current which is set up.
Yes. Now, there are practical values to which this can be put, Earl. Many houses and buildings are heated by a convection water current. They're in the basement of the building. There may be a furnace that heats a tank of water. The water rises through a pipe. It flows through the various rooms of the house and back again where it's heated again. We have a convection current of hot water.
Well, incidentally, the radiators, of course, are the just extensions of the pipes. What they do is to give a larger heating surface so that the house or room will heat up much more quickly.
That's right. And, of course, we have another kind of convection current in the house, too. Around that radiator, there's air. And this air is warmed, and as it's warmed, it expands and it rises. And then the cold air comes in along the floor, and we get the same kind of a convection current we had here, only in this case it's the air going around the room. So two convection currents are involved in such a heating system.
Yes, well, it's certainly obvious that the hot air heating system is very similar to the hot water heating system. In other words, these systems in houses, generally down in the basement, there is a furnace, or sometimes the furnace will be on the main floor, but always there is a duct that comes from that furnace, and it goes in usually at the floor line, somewhere around the baseboard. And then from there, the hot air comes in, and it rises up one side of the room, travels across the ceiling, and down the other side, across the floor, to return to the furnace by another opening in the floor or the baseboard.
Now, here's another experiment in convection. Earl, will you hold that glass cylinder?
I certainly will.
I'm going to light a candle here at the bottom of this box, and then I want you to place the glass tube over the top of it and press it down on that cork so that no air can get in at the bottom. Of course, it's still open at the top. And the candle is burning up oxygen in here, and the warm nitrogen that's left rises up the tube.
Now, there it goes out.
Well, yes, of course, because the oxygen was soon used up, you see, and it needed oxygen to keep burning. Now we'll do the experiment again, Earl, and when you put that in there, put that tube over there, I'm going to put in a little piece of cardboard down in here. Slip this down in here and dividing the cylinder into two parts. But now the flame will burn on as long as you leave that cardboard in. Because what has happened is that the warm air started up, and it started up one side first, and that started a convection current up here, and cold air came down the other side.
Well, how do you know that it goes down this side and up this side?
Well, I don't, Earl, but if I put my finger over there and try both sides, it gets warm here, so I know the warm air is coming up this side now, and the cold air is going down there.
Well, to test that, if we take this out, why then very soon the flame should die down again because the oxygen again will be
yes, if that's tight at the bottom, it will.
Oh, there it goes. I get this back in. I may be able to get it back again. There they
Yep.
come. Oh, there she comes. In other words, we
Yep.
set up a convection current again so that we've reestablished
That's right.
the same thing as before. Well, let's go back over here and look at this boiling
Paper
water
cup.
that we have here in the paper cup and see what's happening. Well, she's still boiling merrily away. Can we dump that into
Well,
the...
see if I can keep from burning myself here.
Turn it upside down, and on the bottom, hardly any indication that the piece of paper, just plain typewriting paper, has been in this flame all this period of time.
Yep.
Certainly very striking.
Well, now, Earl, we come to the third method of heat transfer. Many of you've gotten up sometimes in the morning and seen the sun come up over the horizon on a
Yes.
clear morning. And just as soon as you see the light, you feel the heat from the sun. So this shows that from the sun, heat has traveled with the same speed of light, and that's 186,000 miles a second. So when I said radiation is fast, I meant fast. It travels with this enormous speed.
Now, this that you have over here, then, is a heat measuring device.
Yes, this is a thermopile, Earl. There's a little metal horn, or reflector, and in the back of this horn are a lot of little wires. Now, these wires are arranged so that when heat falls on them, they develop an electric current, tiny electric current. And that current, through these wires, goes to a meter here, which we project on this screen.
Oh, yes.
And you see the pointer of this meter here? It moves when I turn this horn. It's a detector of heat. Now, if I point it at the floor, you see it shows in the center reading a reading of 0.
Yes.
Now, if I point it toward your face, see the needle go over the right?
Is that my face is doing that?
Well, that's because your face is warmer than the,
Oh, I
than the
see.
floor. Now, if I point it at the wall back here, it goes back toward 0 again.
Oh,
Point
yes.
it at my face, it goes up. Back to the floor. Now, in my hand, it goes up again. Anything that's warm is indicated by the movement of the pointer.
Well, that's certainly a very accurate method of measuring heat. Coming back to something that we've known for many years, a heating device, radiant heat, the old-fashioned fireplace. Of course, down at the bottom here is the where the fire would be, and then we have a chimney that comes up here. The important thing about the fireplace is, again, convection currents. Most of the heat comes up here, and by radiant heat, or reflected heat, we get the heat coming out into the room by means of such things as fire bricks in the back of the fireplace.
That's right, Earl. And of course, the radiant heat is what heats up the room. All of the convection currents are up the chimney, and that's fortunate because in that warm air is a lot of carbon monoxide with poisonous gases. And it's a good thing they do go out the chimney. When you face a fireplace and the fire is burning brightly, you'll feel it on your face. And if you turn your back to it, you'll see that the heat is cut off from your face. So we get there an indication that the radiant heat are light waves traveling, and when they hit your face, they're absorbed or hit your body and changed into heat.
So what we have then in our fireplace at home is very much the same sort of thing that we saw demonstrated in this experiment a little bit before. In other words, convection currents going up the tube, and without the convection currents, of course, you wouldn't be able to have a fire in the fireplace any more than this flame would be able to stay there for just a slight second. Now, there's one other type of heating that we haven't mentioned yet, and that's panel heating. It's a newer thing that's just come in, and according to engineers, it's very, very satisfactory and economical. Now, just how does this work, Harvey?
Well, in panel heating, Earl, you have a similar principle to the fireplace. You have a large area that's warm, like the brick walls.
Yes.
Only here, you warm the floors or the ceiling or sometimes the walls by hot water in pipes. This warms up the whole floor area, the ceiling area, and the warmer areas radiate heat toward the people, the occupants of the room. Even though the room may be quite cold, this radiant heat, when it hits your face, hits your body, it's absorbed and becomes heat, and you feel quite comfortable.
Well, this final experiment that you have over here, this gear that you have is certainly very interesting. Those big reflectors, just what is all of this gear now? Can you give us an idea as to how this works, Harvey?
Well, Earl, here we have a large metal reflector, the kind you have in a searchlight. And at the focus of this searchlight mirror, we have one of these thermopiles. Now, way over across the room...
Way down the other end of the laboratory, about 30 or 40 feet down there, isn't it?
Yes. You'll find another mirror down there. It's just like the one we have here. And Bob Bell has a candle flame ready to put in this mirror. Now, when he puts the candle flame at the center focus of this mirror, it acts like a searchlight. It reflects the heat rays as well as the light. And we have a beam of heat rays and light coming across to this one. Here they're again reflected and come into the thermopile.
Oh, yes, now we'll see it on the galvanometer there.
And we'll see it on the little pointer of the galvanometer as it moves. Now, Bob, if you'll put the candle flame in, we'll watch the pointer. See it move over, Earl?
There it goes over.
That shows it's receiving heat here. Now, will you take the candle flame away, Bob? It come back again?
Coming back once more. Can we do that another time?
Over it goes. Now take the candle out, Bob. See the pointer come back again.
Well, just how far could you separate these reflectors now and still get that sort of a reaction on this meter?
Well, Earl, we could put that candle flame 100 feet, a mile, 2 miles, 5 miles, even 50 miles away if it was a clear day, and we could pick up the heat from it and bring it over here and receive it. As a matter of fact, astronomers use thermopiles to detect the heat radiation from stars, believe it or not, millions of miles away.
And then they mount equipment, something like this, in their telescopes and are then able to get a reading.
Yes, they reflect the light or through their refractor, bring the light to a focus from a star on a little thermopile and record the current from it and measure the heat radiated by a star millions of miles away.
Mm-hmm. Well, this is certainly one of the most accurate pieces of measuring equipment that I've ever seen. And looking back over these demonstrations that you brought to the laboratory, it seems to me that it boils down, again, to these three basic issues. First of all, conduction. Secondly, convection. And third, radiation. And no matter where we turn in our everyday lives, we're going to come up against these factors that have to do with heat.
That's right.
Well, I want to thank you again for coming to Science in Action to bring these wonderful experiments. And I see your assistant, Bob Bell, is still wrestling with a mirror down there. Thanks also to Bob for helping with these demonstrations.
It's been a pleasure, Earl.
Now, I'll be back in just a moment with the animal of the week. This is the skull of our animal of the week, and as you can see from those large teeth, it's a rodent, a burrowing rodent, and directly underneath it is the size of the newborn youngster. Very, very small, just about the size of the skull of the adult. You've probably guessed what our special pet is that we have here in the laboratory. It's a pet California Gopher. This one happens to be the special friend of Bill Amsball. Bill, you have a carrot there. Would you see if you can put it down in here? And what do you call him? What's his name?
Dig.
Dig. Oh, fine. Put it over here, and let's see if he's interested in it. This is unquestionably one of the tamest gophers that I've ever had an opportunity to see. He's not quite sure whether he likes that or not, does he? Oh, he's pushing it over in the corner there. How long have you had him as a pet now?
Oh, about a year.
About a year. I'm going to put some of this down here over on the side and see what happens very easily now. Yeah, there he goes. See if he's interested in that oatmeal. I know sometimes he fills these pouches with that. Of course, gophers don't see very well. They do hear, however, extremely well, so that if you happen to come upon one that's working in your front lawn, if you don't step very carefully, he'll know that you're there, although he may not be able to see you. Notice this very short tail. Now, that's quite important to the gopher. He's a little bit, didn't want me to demonstrate that tail, but notice how short it is. That's, again, quite important to the gopher because it enables him to run backwards in the burrow. Oh, he's washing himself there now. Oh, you cute little rascal, you. You know, gophers make wonderful pets, although when we find them in our lawn, we usually want to get rid of them. Now, not all gophers have the appearance of this fellow. I'd like to show you some other color patterns. These are study skins. This is a Milano. This is a desert form here. You can see the difference. And here's an albino. Now, in the eastern United States, they have a gopher that is somewhat different from our western one. Here are the two types, and the main difference is in the size of the front feet. Notice the size of this big foot. This is the eastern gopher, the smaller size of the foot of the western gopher. Principal differences between the eastern and the western gophers. Well, let's see what our fellow Dig is doing here again. Seems to be quite interested in this. How often do you feed him, Bill?
Oh, about twice a week or so.
Twice a week. Well, he's really a good pet, and this is his normal cage that you keep him in. Well, I hope you'll keep us advised as to how Dig does in the future, and thanks very much for bringing him to Science in Action. Now, here's a type of equipment that we'll have an opportunity to examine a little bit more closely on our next program when we look at our radar defense system. Our special guest on the program at that time will be Brigadier General Andrew of the U.S. Air Force. We hope you'll plan to be with us then. Thanks a lot.
You have just seen another in the fascinating television series, Science in Action. Science in Action is produced by the California Academy of Sciences under the supervision of Dr. Robert C. Miller.